Hello YouTube. Today is part 2 of my Logisim 4-bit computer tutorial. But to start the video off, I had a couple people in the comments ask, how do you load a Logisim library? Well, I want to show you. So I'm going to do it with my library here. So we're going to go to my website and download the library, which if you're interested in my Logisim library, you can get it here. And just save it wherever you want. So I've already downloaded it, so I'm going to replace it. So then, once you're in your project, I recommend opening your project first. So, oh, wrong one. Oh yeah, right one. Never mind. Okay, so what you gotta do here is go to project, load library, jar library, and you go to your desktop and find it. So once you've loaded it in, you'll see it appear here, but I loaded it in twice, so yeah, that's the old version. So I'm gonna get rid of that. Crap, I forgot. So we're going to unload libraries. So now we have the new version and the new version only. Now, where's file explorer? Nah, wasting my time. Well, now that we have it loaded in, we have all the parts that we would normally have. So yeah, and I need to update this with the new version. So I'm just going to close it out and restart it. That might work. Nope. Sorry for this. But I want to put it in my new version, which will make it easier. Okay. You don't have to do this unless you've already loaded it. Okay, fine. Just file explorer. There we go. Now if we start it back up, it will have the new version you should. Oh, rename it. Uh, oh, I named it. There we go. Bah. Oh, I didn't know all the new parts. So now we can get rid of this since it has the new version in it. So we'll do that. So inside here, I got the new binary to BCD converter. This is a 4-bit computer, right? Probably. We'll put our new binary to binary code decimal converters in, which are a lot better. Now you can go and make a custom part that does this, but I'd rather just code me up one since it's quicker, in my opinion. I use my own library. Okay, so now that we got our displays here, and our CPU fully works, our ALU fully works. All ALUs need a cache system, because what's the point of adding and subtracting numbers when you don't have any numbers to add or subtract? That's just common sense. So what we need to add in now is we need to add in a memory. So All of this I'm going to put in its own circuit. And I'm going to call this circuit the sub CPU because it's basically going to be a smaller part of the CPU. So we'll need an ALU, and luckily Logisim has this nice bit of memory here. Now, what you could do is you have these two options. You could just use this RAM, or you could use individual registers. We're going to go with the RAM, but am going to show you how you do it if you use individual registers. We'd have something like this, a 4x4 matrix of registers. But here we're just, since this is much more efficient method, we'll just do that. So we'll put our ALU and our RAM roughly right beside of each other. So let's change that to have separate load and store ports. So one thing I like to do, because I don't really like controlling the extra load port, is whenever it's not storing something, we'll load. Because there's really no point to, really, I think that's the most efficient way of controlling it. And for clear, we'll set that to the same as a reset pin on here. So what I'm doing here is I'm just busing it, which I think makes it much simpler. So here we're going, we don't. Here we're going to need a registry on our address. So our address will always be constantly set to something. So, nope. And we'll have that go to its own. Put that on there. Okay, so now we got our address system and our data system done. So here we have our data out. This is our data in for cache. So inside this part here, you're going to have our data, which will come in and will be really important. And we'll just bus that. Completely just bus it. Actually, we'll just rename this to input for simplicity. Or bury up bus. I'm gonna make this system different than my original 4-bit computer, so it's gonna be not alike at all. So instead of my original 4-bit computer, what I done is I had a separate buses for everything. I had a ALU bus and RAM bus and a regular data bus. So instead, what I'm going to do with this system is I'm just going to have one bus, which I can load to and store to. So we'll set that, we'll call that bus in, and we'll also have a bus out. So yeah. So what this will do is we could just write and set these buses. So we'll also have some pins. So we'll have set ALU A, B, and opcode. So that will be for our setting of the ALU values. So where's our data here? Now what do we have here? Flags. How many bits was our flag again? I forgot. It's been a while, and I don't really have much free time to make these videos. So, yeah. We'll make our flags 4-bit. So we'll just have a not did version of all our flags. You'll see why I'm doing this in a second. Where is the multiplexer? Right in the plexers. There we go. And we turn off our enable pins. We don't need that. What else do we need? Oh, yeah, we need a splitter. So our fourth bit of our thingy bob will be our knot. So, yeah. Set that to 4 bits. Yeah, I know it's broken. I'll fix broken this in a second. I just started something. I'll get rid of. So, yeah. Now, if our third bit is on, what should happen is it should dot down. We'll test that real quick. Yeah, sure. Yeah, that works. So it gives us a better system, I think. I was going to do this totally differently when I first planned out the video. And as you can see, I don't do very much planning for these videos anyways, but when I first planned out the video, I was going to do this completely differently, but I decided I like this system more. It sounds better in my head. So I think, and also, if I'm not mistaken, real computers use this system too. Like legit computers, like computer that I'm using to simulate this computer section. Okay. No, don't do that. That's annoying. Wait, what? It shouldn't be a 1 or 0. Okay. Yeah, that's right on flag. Here's our data. Okay, so yeah, that's about right. Okay, so now that we have all this boring stuff, we need more boring stuff. Less explanation right there. And also, we need a registry here because that's not going to work right. I can always sense it. My super sense is tingling. There we go. I'll go to our bus. So now we'll have a set data pin and a set cache address pin. This video is probably going to be a lot quicker than normal since I kind of covered all the basic fundamental principles you need to know in my first video. Sorry about that. Sorry about that. I had to answer the phone a second. Hey, anyways, where was I? Set cache data. Okay. So here we'll have a set cache and a set cache address. But yeah, if you don't know, here I'll write down some quick little shortcuts here, and I'll just copy and paste these. Okay, Control plus C is copy. Control plus V is paste. Control plus X is cut. Control plus Z is undo. I think that's all I know. And if you're running Linux, that's terminal. Speaking of that, if you're running Windows and you have auto hotkey, you can have a script that does that. If you don't know, here is the script. And what this means is that's Control, that's Alt, and that's T. And then that's a declaration statement. It's going run command.exe with the command title, command prompt, and clear, and call directory ... because it automatically resorts to this. So yeah. Actually, I like this more. There we go, that should be a little better. Yeah, I like that more. Sorry about that. Don't give me auto hotkey. I always get lost whenever it comes to that. Why did I have this again? I mean, this register. I'm an idiot. Sorry about my idiocy. There was no point to that. So, yeah, I just realized that. What I can just do is that, and then have that running to the store pin and the clock pin. There we go. That'll do. So, chip select. It's really I can turn it off. Well, there's a way I can turn it off. Boom. It's always a nice way to turn things off. Set on the one. Okay, so now that we have all that, yeah, that looks about right. So now we have our data out. Oh, I need a reset pin. Forgot about that. That was no name for that. 1-0. Okay, so whoops. That looks a-okay. Where's Microsoft Paint? So here's what I'm thinking of a system to do here. Is in my old computer, I used a system where I just had an instruction that every instruction had one use and one use only. I don't like that system because in a 4-bit computer, it's a pretty awful system to say the least. Because when you have every instruction doing one thing and one thing only, well, they're going to run into some problems because you're going to run out of instructions. So here's what I'm thinking. So I have registers, right? We'll have some registers. Let me do this. What? Are you telling me Control C, Control V don't work in Microsoft Paint? Okay, so that would be our internal CPU register. Again, No, one of these would be your internal CPU register. That is amazing. Okay, I take back. I think Microsoft Paint is good. So yeah, you guys can fight me all you want. But Microsoft Paint for the win. This right here will be our internal CPU. Okay, that'll be our internal, and this will be external. So behind each of these, we'll have some more squares. Okay, that's it. I can't use Microsoft Paint. It is awful. Okay, sorry about that. I can't use it. I thought it would be manageable at first, but no. So here we'll have our internal register. Oh. And here will be our external register. So here we'll have some individual registers. Oh, I forgot about something. Um, yeah, so that's real useful too. So we have all these little registers here, and oh, well, that's weird. Oh, maybe select pixels. That makes more sense. Oh. Ignore the transparency there. That's just where it's weird. So text. So this will be your ALU. This might be our cache. This could be secondary system. I don't know. RAM. And this could be program. So here, this will be internal. Oh, where'd my text go? Wasn't writing white. Oh, I forgot. Yeah, this is weird. I'm not used to Paint.net. Internal CPU registry. Now, granted, this system is definitely going to be slower. It's probably going to be better in the fact that we can control more things with using less instructions. Now, I think the term for that is MISC. Well, actually, yeah, it is MISC. Minimal Instruction Set CPU. That's what it stands for. So here we'll have external. I forgot. It's weird with the selections. So the reason I'm making this the reason I'm making this chart here is not because I want to get 10 extra minutes or whatever on the video or anything. It's because I want to show, if Paint would let me, what I want to do with it. Oh my god. Oh, I don't know how to use this utility. Okay. No, I've used this to make tons of icons. It's been a while. I'm gonna make icons for my programs. Okay, anyways, so here's some stuff that we could do. So I'm going to have a bunch of blocks here because this is where it's going to be important. So here we could have user input slash user output, a graphics processing unit, let's say text system, EMMC. If you don't know what that stands for external memory management, I guess. I just made the abbreviation up on the top of my head. It's all legit. External memory management controller for external memory, of course, or a DOS could be a good system. MPU, external mathematics processing unit, so you can have extra math. It's quicker, and all this which we will control via the glorious instructions there. So, let's start making an example of instruction set. We need an idle command. So that'll be one. And I have a software halt command, which means halt, stop the CPU until we get an interrupt. Well, actually, it basically means halt, just stop everything for some amount of time. There yet? We just won't have that. So, now that we have some basic stuff, wait for interrupt, reset, that kind of stuff. But what do we need? So let's start brainstorming. We need to talk. We need a system to talk to these two registries we've just created. So, how would we go at doing that? Now, what we could do, we could have something like send data. So let's say we have our instructions in a form of instruction, I can spell instruction, and then the data. So whenever a program's loaded up, it comes with the instruction and then the data afterwards. So the next clock's very up, we could have multiple datas. So data 1, data 2, data. Sorry. So we'll have an instruction, then a data, and then a data, and then a data, and then another instruction, then data, and then data, and then a data. Now, that's a little bit inefficient. To be honest with you, to be quite honest, I think that's a bad system. Because if you think about it, three-fourths of our whole entire program could possibly just be zeros, just nothing. So our programs, this could end up making our programs way too big, way too big. So instead, what we need is we need a system that will. We could use this system, but it's going to take a lot of memory, and this is a 4-bit computer. It's nothing like we have today. So I think this is a very inefficient system. So what we need to do is, since I don't already have a system in my head, we got to brainstorm a new system. So what I'm thinking is, instead of having instruction data, we just have an instruction. It's instruction sent, and on a separate bus, we'll have a data. We'll have two buses, an instruction and a data. And that sounds pretty simple, and I think that could work. Now, again, I don't like this system because, or hurry up, we just have instructions and data. So we'll have some commands here. So I think we should have a put command in a get. Put data in selected registry. We'll change this to 4 because I think I want 3 to be select registry data. So we'll have put data in selected registry. So what we could do is we can put our data in the selected registry. So let's say we're doing, let's say, I don't know, we have our internal CPU registry. So we could select that register or that register, the internal right here or this. And then we can put a number inside here. And once it gets that number, it selects either ALU, cache, RAM, or program. And then once it's got that number, the next number you put in it, it'll be whatever it wants the ALU to do, and so on. So we'll have slots in our registry. So we'll have 2 slots, a data and an instruction slot, right? So we can also have put data and registry So put data in registry instruction slot. So, let's say we want to get that. So we want to set data to get registry. So each registry will have 1 output slot. And we can set our data to that. Or we can also have a set. That sounds like it will work. To registry out 0 slot. And also a second slot for data out. So we can set our data to the registry out 0 slot and set our data to registry out 1 slot. That sounds like a good list of stuff right there, what we have. And it's very small instruction set. And I think we could do anything we want with this instruction set. So we have a data, which we can set from the registries. And we have an instruction. So actually, I noticed a bug. I don't like where this is here. And I don't like having a RAM there. So I want to get rid of that. That didn't work. So I don't like RAM there. That could be on our external stuff. So we need more instructions because this is a big waste of an instruction set. So what else could we do? So we have these registry systems. How do we get instructions to the CPU? Hmm. Thinking. So we pass an instruction. It can put and set data, get and set data. We select a registry and we go on with our lives. So now what? What else do we need to be able to do? We can jump. So this covers jumping. So you know how you have your classic move instruction in machine code, right? So the classic move instruction. I think it's mauve, right? This right here. So you have this classic instruction in machine code for x86 machines. So mauve. That's and you could do anything with this move instruction. And when I say anything, I mean literally anything. There's a DEF CON video on how he makes a program that takes a C program and turns it into only, and when I say only, I mean only move instructions. Nothing else but move instructions. So as long as we got this move instruction, that's all that matters. And yes, jump can be done with a move instruction. So we have move. So when we want to move data, what we could use is that's all covered by our put and set system. Now, what we jumping. So when we set data to, so when we put data in registry, so we can select program as our registry. We can put data inside of it. And let's say we put 8. So we put 8. What that would do is once we put that 8 in there, it will set that as the jump address. And then we can set put data in registry instructions dot, which is 1, which will automatically jump. Will jump to what we put in our address slot. Problem is what if we wanted our address to be an 8-bit address? This is where we're limited. A 4-bit computer can only have an internal 4-bit bus. Otherwise, it wouldn't be a 4-bit computer. And this is a humongous limitation. Because what if you want to do more than just use 4 bits? Like, what if you wanted to have a bigger program that had more than 16 instructions? That's something we're limited. We're only limited to directly a 16 instruction program. Now you might be saying, oh, well, if that's the case, how would you accomplish anything? And if you look on YouTube, let's just go on YouTube, for example. We'll search 4-bit computer. So let's see if somebody has built one that can handle more than 16 instructions. Okay, just take my word. Somebody has built a 4-bit computer that can handle more than 16 instructions. Now, with this system, it's going to be a little bit difficult because we're going to need an external memory management controller, no matter what. That's just, if we wanted more than 16 instructions, our first 16 instructions need to give instructions to turn on the external memory management controller and start reading from it. So for example, we take our external memory management controller. We have an instruction inside of it called read line. And what that read line instruction does is it takes all of that data, sends that to our program, and then boom, our program's loaded up, or at least part of it. The first 16 instructions are. And then once it gets that 16th instruction, we we go to our, our first program, and it loads the next 16, and so on, and so on, and so on. So that's what I want for now. Now, later on, we can continue developing this instruction set. But for now, I'm going to have to end the video since it's reaching about an hour long. And we're going, but before we end the video, I want to finish the sub CPU. That's what I want to do. So here we are, we're inside the sub CPU again. So now we have an idea of what we want to do. I did have an idea beforehand before making this video, but to be honest with you, it was pathetic. It was an awful, pathetic idea, and I want to have a computer that can do a little bit more than that, than what we wanted to do. Our instruction set was more like it was not MISC at all. It's not designed to be that way, because I wanted to do it off my old 4-bit computer, but that wasn't going to work, because my old 4-bit computer had one fatal limitation, and you can't do very much at all on it. So now we're going to have some outputs here. So we need basic outputs. So we'll have our flag. Simple as it is, but yet so useful. One of these is bound to be flag. This is our flag right. One second. Okay, so now that we got our flag out, I want to have some pins here. So send out set bus So we want set bus to cache and set bus to ALU to give us that little bit of a boost on our instruction set. Because we want this instruction set to be small and useful. And if we can manage that, that's all that really matters. We want a very small and very useful instruction set if we want to build a good computer. Now, I also want an overflow flag, because what if we want to set our interrupt? What if we have something like an interrupt controller or an interrupter on our external registry system? Well, let's say we wanted to interrupt on an overflow, and then we can tell the user, oh no, a program overflowed. What do we do now? And then we can have a better debug message for the programmer who's working on this. That would be a lot better than just watching that pin to see if it turns on or off. And if we're going to run this at a decent clock speed, which we're going to need to do since we have a MISC instruction set, yeah. That was pretty magic, wasn't what I just did there. Oh yeah, I forgot to tell you guys. I added some square gates inside my. Oh, I need to make an updated version again. I'll get on that. The newer version has square AND gates, square OR gates, square XOR gates, all the square gates you can think of. So yeah. Let me look at that real quick. Minimize, clip. Sorry. Uh, yeah. See, I'm adding in this square one here. And this export that. Oh, I just exported as the wrong jar file. Oopsies. Oh, yeah, I didn't realize I done that. I think I stored it in my electronics folder. Linux, projects. There we go. There we go. Problem solved. I'll upload the new version to GitHub. So close that. Save it, reopen it. Yeah, see? Much better now. Okay, sub CPU. So, now, we got this word right. Now, I forgot. Yeah, I did tell you guys what I'm wrong word right. We got this word right. Now, what we're doing here is, let's be realistic. We can't really, we need a better setting system, if that makes sense. We need a set system that we can set better. Because everybody knows how Logisim is here. Everybody knows how it works, or at least I hope you do, because it's a little bit difficult to make a computer in a program you don't know how to make a computer in, because you don't know how the program works. Well, see, Logisim has a thing, or you can't have two wires set at once. Now, what I'm going to do is our bus out will be a big OR gate going to, oh my god, oh my Jesus. Ah, look at that. That is awful. Why does it, oh my, are you serious? Why did they even do that? That's stupid. Now look at what I have to do. Satanic. Honestly, thank Carl Bunch put that in there for purposeful reasons. Okay, anyways, after that little conniption, I'm gonna use my square word deck because might as well put it on narrow. Yeah, look at that. Now we got a really small guy. And I want to set this to 4 bits. The reason I'm using my own is because I think it's better. That's better than a lot of some gates. Probably cause my computer to crash somehow just now. Like, honestly. Okay. So, we have that. Did I add my buffers? No, I didn't. Actually, I forgot about the multiplexer. Sorry about that. Could have just used this. I don't know. Yeah, I'm really good at overcomplicating things. Honestly, I could get a 10 out of 10 for overcomplicating the simplest task. Like 9. I mean, I did not need a separate float. I did not need that, did I? There we go. Problem solved. So now we got 2 multiplexers. Now select where to go. So. So if we want to set our bus to the ALU, this needs to be 0, and we need to turn valve turn on. So let's have an OR gate here to decide that for us. Now I'm just going to use a regular portrait. So, so, actually we need an end gate on the portrait. And you'll figure out why. Don't even worry about it. Yeah, no more pins. Okay, so first off, we got this, and it goes to our set bus to ALU. That needs to be an on. Well, the last two need to be off, so we can negate them. Now, you might be wondering, oh, what am I doing here? I'm negating it. Well, the reason I'm... yeah, I'll do that. The reason I'm doing that is because it's just common sense, okay? Learn Boolean algebra. I can explain it. So if that's one, I don't like that now. That won't work. So never mind. Never mind. Ideas out the window. So we got them two, right? Makes sense. So this is 0. So if this is on, this needs to be 0. If this is on, it needs to be 1. Okay. Well, that's easy to set up. I might be completely overcomplicating this, or I might just be really stupid. I don't know yet. I think I'm completely overcomplicating it. I honestly think this method would just work. Oh god, that wouldn't work at all, would it? I am completely overcomplicating this, aren't I? I could just do that. I mean, that should have been thought of so much quicker. I have a mental deficiency, I think. Oh my god, I'm retarded. Kill me now. I honestly think I have a mental deficiency right now because the fact is, I overcomplicated that so much more than what it had to be overcomplicated by. So, if either of you want, we need to not that put that on it. Okay. Actually, never mind. I overcomplicated that just now. So if it's set bus to cache, well, then we'll pass that. If it's that, well, then we'll do that. Okay, so I think that's our sub CPU pretty much done. Oh, you know what? Let's stringify it. That's a good term. Oops, I don't know why I just done, but whatever. I'll accept it. There we go. The reason I'm shrinkifying it is just to make it look better, like if you have a smaller screen resolution or something and you download this. I haven't even put it up for download. Yeah, I'm not going to bother. I'm too lazy to actually do that, and I'm not going to really bother with it, so yeah. So yeah, here is the fully done circuit, which is, I think it'll work. Well, everybody knows what do you do when you think you're done. Well, since nobody answered, I guess I'm gonna have to answer my own question. Yeah, test it. Okay, let's test it. Okay, so we have our. I don't like that. I don't know this phone now, so you have no idea. My God. I also don't like how that's like, there we go. How much? 55 minutes? Half of it's bull crap where I haven't really done anything. I bet the other half is me doing this fancy diagram. Okay, anyways. Anyways, after I've wasted all your time, now for the fun part of testing it and finding all the bugs, which if I do find a bunch of bugs, which I highly doubt I will, but if I do find them, I'm not going to fix them in this video unless I have 4 minutes of extra time, which I'm using up. So, let's look at our ALU opcodes really quick. I forgot I made a file with them all, didn't I? No, I didn't. So, adding is, what is that? That is 7. So we're going to try and add 1 plus 1. So, is that 7? No. That's 7. Okay, so we're going to call set ALU opcode. So now we're going to do 2 plus 3. And we're going to... Yay! It worked. And we have a flag. I don't know what my flag is, but the good thing is it's working. And that's all that matters in life. I'm just kidding. So, we have 5. 5 is a good number. I like 5. You know why I like 5? 5 means it's working. So, yeah. Now that we've successfully fixed all of our bugs, we need to test the cache. So, let's start testing the cache. So, I'm going to reset everything as well for good measure so we have a clean test. I'm going to put 5 as our cache. So, boom, we have 5. So now I'm going to set that to our address. I'm going to set my... Oh, never mind. That was just my mistake. So now we can set our bus to our cache value. Suck here. Okay, so I think I know what's wrong. So remember when I showed you about square waves, right? How they have... Remember when I showed you about square waves? So that's me and get a square wave. Okay. I don't think I showed you about square waves in the last video. Okay, so you have this beautiful square wave, right? Well, on default, when you trigger a timer, it starts off on this rising. So as actually real square wave. Let's get an image of a real square wave. Now the reason, good picture. Here we go. So the lines here are the real square wave. So we'll take the purple line. That looks like a good line. So as you can see, you have a little bit of time. The black, pure black, is an ideal square wave, and the sine wave, that is the worst kind of square wave you can get. And I've seen electronics with a square wave that looks like the red line, or at least what it was supposed to be a square wave, which wasn't. Anyways, so let's look at this gray one right here, or the purple one. So as you can see, you have this rising edge. It rises up, and then it kind of stays out, and then it falls. So instead of, we're triggering on the rising edge, but our RAM is sending values out on the high level. So we're setting it here, but we're only getting it here. So what we need to do is we need to set it here. So now we know. That's what's wrong. Yeah, that's going to actually show you in action. Don't need to do that, do I? Now I'm going to try. Boom! It works. So, it seems as if it was working. So we'll try multiplication. And I'm not going to stay that's 8. So we'll say ALU opcode, and we'll try 8 times 8. Now, obviously, we're getting overflow. Now, let's look our overflow. Okay. So 8, 16, 32, 64. Now, as a sanity check, because you should always do sanity checks in programming or electronics, we're going to do 8 times 8. Okay, well, that seems like it's working. It's a good sign. And the reason I've done that is because, seriously, just do sanity checks. Like, honestly, I made the dumbest mistakes because I didn't do the sanity check. Like, when I was working on a web server I'm working on currently, basically what happened is I made a super small mistake and I looked over and over and over, and I didn't want to do it sanity check because making Java sockets, I just don't like Java sockets. I hate how Java sockets work. They annoy me so much. So I never done a sanity check, but if I would have done a sanity check, I would figure out the problem was with Java sockets and I was creating it wrong. I never done the socket dot accept method. So yeah. And that's why it wouldn't have set things lines. So we have successfully made our sub CPU and it is working. So next video will be the fun part. Fun part, I say it in all truthfulness. Oh yeah, I lied when I said fun part. It's gonna be awful.